How you doing tonight?
Good, how are you?
Good. So have we moved on to sum and difference identities yet?
No.
Okay. We must be solving trig equations then.
Yeah, I still have some solving and verifying ones.
Okay. Shoot.
Okay. So the first one says 1 plus tangent squared of x over 1 plus cotangent squared x equals tan squared x.
Equals what?
Tan squared x. Tangent squared x, sorry.
Okay. What's the identity for 1 plus tangent squared x?
1 plus tangent squared x equals secant squared x.
Okay, so I can replace that with secant squared x. What's the identity for 1 plus cotangent squared x?
Equals cosecant squared x.
If we turn both of those now into sine and cosine, what do we get?
You get 1 over cosine squared x and 1 over sine squared x.
Like that, right?
Yeah.
Now flip and multiply to turn it into sine squared x over cosine squared x, and that's equal to tangent squared x.
That was easy.
Yeah. It's usually when you can immediately replace two terms with one, that's almost always the way to go. And I could do it top and bottom here. In other words, there wasn't anything to do, but that was an automatic first step because I can immediately replace that with one term. Same with that. It's a secret of verifying, is always try to be reducing two terms to one if you can.
Okay. Let's see what else I'm solving. It's just really verifying that I need to work on. That's what's hardest for me.
Okay.
Okay. This one says
solving can introduce all kinds of new aspects that are not involved in verifying. In other words, usually when you solve trig equations, it's more algebra than it is trig. If you think about it, it's solving an algebraic equation, only it's in trig. So let's make sure we don't ignore solving them, because there's going to be some tough ones to solve. I think in general, solving is more difficult than verifying. But maybe not for you. So let's work on whatever you want. Well, truly, it may not be that way for you, which means we should work on verifying.
Yeah, and then maybe a couple solving. I don't know.
Okay, all right.
Okay, so this one says 4 cosine squared theta plus 3 sine squared theta.
This is a solving problem.
Verifying.
Really? Gosh, I was wrong. I thought I was so smart. Okay. Go ahead.
Yeah. Okay. And then equals 3 plus cosine squared theta.
Okay. Everything is in cosine except sine. Can we turn the sine into cosine?
Yeah.
In other words, that's usually what you want to do. I recognize that I got a cosine squared there, I got a cosine squared there. Well, if I can turn that into a cosine squared, I'm going to be 90% home.
Okay.
Okay, so let's do it.
And it would be theta plus 3 over cosine.
No, 3 times. What's the identity for sine squared in terms of cosine?
Oh, 1 minus sine equals
1
cosine
minus
squared?
cosine squared. That's the same as sine squared. In other words, if you have sine squared plus cosine squared equals 1, well, the thing you usually end up seeing is this. In other words, when they give you problems, they're going to show you this and expect you to know that that's equal to sine squared, and vice versa. Okay, so in place of the sine squared, I plug in that. Now it's just a question of distributing and simplifying. And that's equal to that.
Oh, that was easy too.
Yeah. And they're not always hard, or I'm not terribly fond of the ones you have to multiply by the conjugate, stuff like that, because I just think that verifying trig identities should be all about knowing your trig identities, not knowing that you have to multiply by the conjugate. You know what I'm saying?
Yeah.
In other words, the only purpose of these things is to teach you your trig identities. And that's a trick that doesn't really have anything to do with trig identities when you multiply by the conjugate. In other words, whenever you see something like this in your trig verification, well, I can't do anything with that. That is not equal to any kind of identity. But if I were to multiply it by 1 plus sine of theta, now it turns into 1 minus sine squared, which I can replace with cosine squared. So by taking these two terms, multiplying by the conjugate, I turn it into one term. So that's kind of one of the secrets of trig identities, is knowing when to multiply by that conjugate. All right.
I have a problem I think might be kind of like that. Well, that I just don't know what to do with it.
Yeah.
So this one is 1 minus sine theta
There you go. Yeah.
over secant theta equals cosine cubed theta over 1 plus sine theta.
So the most logical step to do when I see that is to multiply top and bottom by the conjugate of the top. The reason being, and there's also another secret here. So we're going to multiply by 1 plus sine theta all over 1 plus sine theta. And the secret, whenever you multiply by the conjugate, do not distribute the bottom. The top turns into 1 minus sine squared, which it always does when you multiply by the conjugate. And the bottom leave as this. Do not distribute it, because if you distribute it, you'll end up having to factor it out again. In other words, leave it like this. You with me?
Yeah.
Tops replaced by what?
It would be 1 minus sine squared theta.
Replace that with one term.
Cosine squared theta.
Now what can I do with that secant in the denominator?
You can turn it into, you can turn it into 1 over cosine, and then you have to flip.
Right. So you can turn that into a cosine in the numerator. That turns this into cosine cubed. Okay? And pretty much wherever you see something like that, you can kind of do it. In other words, if I saw notice that if I saw this, doesn't help to multiply that by the conjugate. If I multiplied that by that, I end up with 1 minus tan squared, but that's not an identity for anything.
Yeah.
Notice that the identity would come from seeing something like secant squared minus tan squared. That's equal to 1. But 1 minus tan squared is not equal to anything. So I would not, if I saw 1 minus tan, I would not think about multiplying by the conjugate because it doesn't accomplish anything. It turns it into that, but I can't replace that with anything. Now, if I had the following, if I had secant minus tangent, I might think about multiplying that by secant plus tangent. Because what does that leave? Secant squared minus tangent squared, which I can replace with 1. All right, so what's the next problem?
Let's see if I can find one. Okay.
Let's solve an equation before we run out of time.
Okay. So I have a couple of those too.
Okay.
So this one says 2 sine squared x minus sine x equals 1.
Okay, if everything's in sine, and one of them's squared and one of them isn't, we have a quadratic. So let's set it up as a quadratic by moving everything to the same side and factoring it just like it was a polynomial. Instead of, in other words, we're going to factor this the same way we factor this. Instead of using x, we're going to use sine x.
Okay.
Tell me what goes everywhere.
Sine x minus 2 and sine x plus 1.
Okay, this got to be 2 sine x.
Oh, yeah.
And that doesn't work.
It does not?
Uh-uh.
Hmm.
So let's do it by steps. Start out with sine x and 2 sine x. What do the signs have to be?
A negative and a positive.
Right, but it could be negative positive or it could be positive negative because this coefficient is different. And now the only possibilities are 1 there and 1 there. Does that give us the right answer? Ah, it does. Now what?
And then you have to find what the other term, or no wait, never mind.
We can solve it now. In other words,
Yeah.
now we know that either that's 0 or that's 0. So what's the next thing I should write?
To solve it?
Uh-huh. In
Yeah,
other words,
then
our goal is to solve for x, not sine of x. We got to come up with the angle that makes this all work.
Yeah, so you make each sine equals 0.
Okay, so sine x equals 1. So what is x for that solution? Is this in the unit circle? In other words, are we going from x going from 0 to 2 pi?
Yes.
I thought so, okay. So where is the sine of x equal to 1?
At 90 degrees.
Or pi over 2. Did they define the domain as 360 degrees or 2 pi?
They defined it as 2 pi.
Which means they want their answers in radians.
Yep.
That's the only place in 0 to 2 pi where it's equal to 1. So the other part of the equation says 2 sine x equals negative 1 or sine x equals minus 1/2. Where does that occur? And that's going to occur almost always in two different quadrants. Where is sine negative? Which quadrants?
Sine is negative in the third and fourth.
Third and fourth. So those are the answers we want. What's the equivalent first quadrant angle for this? Where would sine x be equal to 1/2?
In 30 degrees, or pi over 6.
Okay, so we'll write that down. That's not our answer because we're looking for a negative 1/2. What is the third quadrant equivalent of pi over 6?
It's going to be, so let's see, wait, sorry, I have to do it in my head.
Well, here, let me show you a better way to do it. Second quadrant is 180 minus theta, but the other way to write that is pi minus theta. And in the third quadrant, we normally would have theta minus 180, but the other way to write that is theta minus pi. Excuse me, I wrote that wrong. 180 plus theta. Theta minus 180. I was right the first time. Theta minus pi. And theta minus pi has to equal pi over 6, right?
Mm-hmm.
So what's theta? If theta, in other words, this is the formula for third quadrant, so it means theta minus pi has to equal the equivalent first quadrant angle. So what's theta?
7 pi over 6.
Yeah, that's one of them. That's the third quadrant. How about the fourth quadrant? And in the fourth quadrant, I have 2 pi minus theta equals pi over 6. So theta would equal what?
11 pi over 6.
That's the way I do it. You can convert it to degrees and do it in degrees and then convert it back to radians, but it actually saves 2 steps if you work in radians the whole way. And the secret is knowing what the radian equivalent of that is, and of that, and of course of the 360 minus theta. That's 2 pi minus theta. So we have 3 answers: pi over 2, 7 pi over 6, and 11 pi over 6.
Can we go through and check them? Because we have to do that for
Yes.
tests and things. I just need to practice that.
Okay, so let's try pi over 2. What's the sign of pi over 2?
Our sine is 1.
Okay,
Wait.
so we got 2 times 1 squared minus 1. Does that equal 1?
Yes.
Okay, so that solution works. Now let's try 7 pi over 6. 2 times the sine of 7 pi over 6 squared minus the sine of 7 pi over 6. Well, what's the sine of 7 pi over 6?
Wouldn't it have to be 1/2?
Negative 1/2. It's in the third quadrant, so it's got to be negative 1/2. So now I have 2 times negative 1/2 squared minus a minus 1/2. What's that equal to?
1. Right, because you have, yeah.
Hold on, I did something wrong here. No, yeah, that's right, that's right. So this becomes 1/4 positive, times 2 becomes 1/2, minus a minus 1/2 equals 1. So 7 pi over 6 works. And let's try 11 pi over 6. So first of all, what is the sine of 11 pi over 6?
1/2 again, right? Negative 1/2?
Negative 1.
Yeah.
So it's the same math. We still know that that equals 1. So 11 pi over 6 works also. In other words, 11 pi over 6 is the same as 7 pi over 6 as far as checking the solutions go. Okay? Good to go on that one?
Yes.
Okay. You got 6 minutes. I'll let you pick whether you want to do solving equations or doing more verifying.
Maybe more verifying, just one more.
That's fine. Okay.
Okay. So this one says cosine theta over cosine minus sine, or cosine theta minus sine theta.
Equals what?
Equals 1 over 1 minus tangent theta.
Well, it's going to be difficult to turn cosine and sine into tangent, right?
Yeah.
But notice how easy it would be to turn tangent into sine and cosine. So let's work with the right side. Now I got everything in sine and cosine. Now it's just a straight algebra problem. So what can I do on the right side now?
You can flip it.
Not yet.
No, because it's not
Two terms. I got 2 terms in the denominator. I can't flip it until I subtract those 2 terms.
Oh yeah, so you have to find a common denominator.
Okay, which is?
Cosine.
What goes here?
Yeah.
What goes here?
Cosine minus sine theta.
How about cosine minus?
Sine. Cosine.
Does that equal 1 minus sine over cosine? Yes, it does. Okay, I got a 1 there. Now you can flip, because now the denominator is a single term. The denominator of the denominator. Once you get it to be a single term, you can flip. It's okay that the numerator still has 2 terms in it. That's okay. But I could not flip that until I combined them. Okay, well, after you flip and multiply, you get what is on the left side over here.
Yeah. Because you get 1 over cosine, or cosine times 1.
Well, when you flip, you get cosine in the numerator and this in the denominator.
Yep.
Okay. What else? Got time for one more, I'll bet.
Okay. 1 minus 2 times sine squared theta over sine theta times cosine theta equals cotangent theta minus tangent theta.
Like that?
Yeah.
Okay. Well, again, I can turn everything into sines and cosines pretty easily. So let's do it. Now it should be kind of clear at this point what's going to happen next. What are we looking at there? The common denominator of what's going to end up over here.
Mm-hmm.
Okay, so let's subtract these 2 over here. There's the common denominator. What goes here?
Cosine squared minus sine squared.
Okay. Now, okay, so at this point, I've got the denominators the same. So the question is that the same as this? Well, that's all I have to prove, and I've got a sine squared there, I got a cosine squared and a sine squared, so what should I do?
You should use the identity.
Okay.
The 1.
Not for 1, but
We'll
for
forget the sine squared.
replace that. In other words, we want to get everything in sine squared in the numerator. We've taken care of the denominator. If I can make everything be sine squared in the numerator, it's going to end up being 1 minus 2 sine squared. What's cosine squared equal?
Sine, or 1 minus sine squared.
Minus another sine squared. That gives you your 1 minus 2 sine squared.
Yeah. Cool.
Okay. So it isn't always correct to turn everything into sines and cosines. But if you have a lot of sines and cosines already there, that's usually the way to go. In other words, we started with lots of sines and cosines on this problem from the get-go. So it's real clear to me that we need to, and we can turn both of those into sines and cosines very easily. So that's really always going to be the way to go. If I had stuff over here like secants and cosecants, now it's not so clear that I want to turn everything into sines and cosines, because there is an identity with tangent and secant. So I might want to go a different way. But boy, when you're looking at half the things are sines and cosines, usually it makes sense, if you can, turn the other stuff into sines and cosines. All right. Sarah, that's probably the last time we're going to be doing verifying trig identities. I doubt that you'll still be working on them next week. But you might be on to harder trig equations.
Cool.
It's okay. Remember, to solve a trig equation, you need to get everything into the same trig function. In other words, if I have this kind of a trig equation, and I got a cosine, I got combinations of functions, then I need to turn this into sine squared, or this into cosine squared, in order to proceed. You can't solve a trig equation if you have multiple trig functions in it. It's very hard. If I have this, that's hard to solve. I got 2 different trig functions. I have no idea how to solve that.
Yeah.
So they're easy to solve if you can get everything into one trig function. And that's what I will leave you with. That's the secret to solving trig equations. All right. I will talk to you next Tuesday, Sarah.
All right. Thanks.
Bye-bye.